Alright, so in this particular lesson, let's find out the height of a binary tree. So the height is essentially defined as the number of edges on the longest path from the root node to a leaf, right? And if the tree is empty, the height is essentially 0. Also, if the tree has only one node, in that case also the height will be 0 because there would be no edges in the tree, right? So essentially the height is the maximum number of edges from the root till a leaf node, right? So maybe let's look at an example tree. So in this particular tree, if you see, the longest path is from root node 1 to node 4 and it goes through 2 edges. So the height of this particular tree is 2, right? So that's the entire question. This is what we need to do. We need to find the height of a given binary tree by this definition. Now maybe you can just pause this video and try to think of a solution. And once you are done, you can just come back and check the solution. Okay, so now essentially we need to find the maximum number of edges from the root node to any leaf node, right? And this longest path can either be present in the left subtree or the right subtree, right? So we need to actually calculate the longest path first of all on both the subtrees separately, right? And then we can take the maximum of the two. And finally, we can just add 1 to this result to account for the edge from the current node, right? And then we just need to keep doing this at every node in every possible subtree that we can have, which will add up the result for the overall tree as a whole, right? So let's actually walk through how we can solve this using recursion. So first of all, as a foremost thing, we will check if the current node is null or not, right? And if the current node is null, then we simply return 0, right? As there are simply no edges for us to count. Else, if the node is a leaf node, in that case also we will return 0, right? Otherwise, we recursively compute the height of the left subtree, then we compute the height of the right subtree, and then we take the maximum of the two heights. And finally, we just add 1 to represent the edge connecting this current node to its deeper subtree, right? Wherever we found the maximum height out of the left or the right subtree. And at the end, we just return this total that we calculated as the height from this node downward, right? So now maybe let's actually walk through this algo step by step on a sample tree, right? So if you see over here, we start at root node, which is 1, right? Now we need to calculate the height of its left and the right subtrees. So we move to the left child, that is node 2. Again, we explore its left and the right subtrees. Now node 2's left child is node 4, which is a leaf node. Since it has no children, we can just return the height as 0. And now we come back to node 2, right? Now the height of the left subtree is 0. And if you see the right child, there is no right child over here. So that is null. So the height of the right subtree is also 0 over here, right? So essentially node 2's height is 1 plus 0 and that is equal to 1 itself, right? And now we move to the right child of node 1, which is node 3. And it's also a leaf node. So the height is 0 over here. And finally we get back to root node 1. Now the left height we got is 1. Right height we got is 0. So the total height is 1 plus 1, that is equal to 2. So the height of the tree is 2 over here, right? So that's the entire algorithm. Now maybe let's see the code for this particular solution. So first of all, we define our node class, which contains 3 fields, right? The data, left and right. And each node will point to its children via left and the right pointers, right? Now inside the solution class, we define the function height, which will take the root node as the parameter. And the base case over here is that if the root is none, we just return 0 because the tree is empty. And then we check if the current node is a leaf node or not. And in that case also, we just return 0 again, right? Finally, we use recursion to find the height of the left and the right subtrees. And then we take the maximum of the two and add 1 to account for the edge to the current node, right? And this is that line which actually gives the height for the current subtree, right? So that's the entire solution. Now maybe let's talk about the time and the space complexity for it. Now since we are visiting each node exactly once to compute the height, the time complexity over here will be order of n and the space complexity over here will be order of h, where h is the height of the tree and this is due to the recursion stack created as a result of the recursive calls that we are making, right? And in case of a skewed tree where all the nodes are actually stacked on the same side, this can actually go up to order of n, right? So that's the entire solution. I hope you understood the entire thing very well. And now I will see you in the next one. Thank you.